really sorry for that. Actually, before that, I was teaching this type of stuff. That's why I may. Yes, sorry. This was all about that, right? I was saying that there is this is the topic what we have to discuss right in this. It consists of five parts: laws of magnetism, magnetic properties, then electromagnetism, and then I told you that forces due to electromagnetism, and then electromagnetic induction. This was what I wrote on that slide. Then general properties of the magnet. There are laws of magnetism. Laws of magnetism are that like poles repel and unlike poles attract each other. Repel and unlike poles attract. So in a magnet, we have two types of poles, a north and a south pole, and a south pole. N for north and S for south pole. So whatever the magnet size is, whatever the tiny or giant magnet you have, it would have only two poles. It's not that you have a different dimensions of a magnet and it would have multiple poles. No. If it is a spherical magnet, it would have two poles. If it is a rectangular magnet, triangular bar magnet, whatever that is, it would have two poles. So that is what the basic concept of magnetism. Then here in this slide, I was saying that 2000 BC in China, it was in old China, it was basically found that there is a magnet, there is a stone which is called lodestone. Actually, later on, if you people take chemistry, you should know that this is an ore of iron which is called hematite. Fe3O4. It is an extract of iron. So we extract iron from it. That's why it behaves like iron. So all those materials which are having magnetic properties, they are called ferrous or ferric materials, because iron is the name of iron is ferric, Fe, right? So ferromagnets, they are called ferromagnets as well, ferro material. So this was its history. Then I talked about that properties of magnet. It has magnetic field around it. It has poles, attraction of the material. When there is a magnetic material or magnetized material would be there, they would be attracted by the magnet. It exerts very small force or no force on non-magnetic materials like woods, and then copper and all that stuff. So here I was talking that earth behaves like a pole. I mean to say that this is, for example, earth. This one is earth. Let's say this is earth, and there is a magnetic field inside the earth, in which south pole is over here, north pole is over here. So earth's magnetic fields are probably from north pole to the south pole. I will explain this in later on in detail, because till now we are not clear about, I did not tell you about the magnetic field lines, but because here is that topic what I have to explain to you. So actually what happens, one pole of the earth is south and one is north. This is magnetic pole, right? So when you suspend a magnet on the earth, magnet of north of the magnet is attracted towards south of the earth. That's why this point or this side where your magnet is pointing its north, that is called magnetic north pole. But in fact it is, sorry, this is called your geometric north pole of earth, because all geometry is based on the direction of this pole. But actually it is magnetic south pole. It is magnetic south pole of earth. South pole of earth. Remember this thing. This is very important
Sir,
thing to know. Yes.
could you please excuse me for 5 minutes? I have to quickly say my salah.
Okay. Yeah.
Thank you.
But you have to go through all these slides after that. Okay.
Of-
Then Here I have explained that force between the magnet. If two magnets are brought closer to that, north repel and north and south attract, like poles and unlike poles. So this is the law of magnetism, what I have explained. That if I bring north to north, they would repel, and if I bring north to south, they would attract. Hence, that like poles and unlike poles concept is there. Then we have induced magnetism. This is very important thing to know. Induced magnetism means when a material is not magnet, but it has magnetic properties. If we will bring it closer to the magnetic field or magnet, it would behave like a magnet. For example, iron nail is there. So if I bring an iron nail closer to the north of the pole, it would be attracted. And I told you why would it be attracted, because it creates south pole near the north end of the magnet, and on the other side its opposite pole north is generated. Now if I will keep this closer to another nail, it would create south on its head and north on its tail. Similarly, if I remove this magnet, then it this nail number one, this is your nail number two. If I remove the magnet, nail number one would also be demagnetized, and nail number two will be released from it. So iron is kept in the magnetic field, it is a magnet. When it is removed from the magnetic field, it is not a magnet. Okay, is it clear?
Yes.
Okay, now I have another important thing to discuss. Okay, so I was at this point that induced magnetism, that north poles are basically producing south on the opposite or opposite pole on the iron, so that it is attracted. So that's why near the north south is produced, and on the other side north, and on the nail too south is produced, and that south induces north on the opposite end. I mean, head is north, head is south, tail is north. Now I was explaining that I have removed this magnet. It means now magnetic, this nail number one is out of magnetic field. So when it is out of magnetic field, so what happens, it is no more induced poles, so it releases nail 2, it falls off. So remember this thing, that induced magnetism is the magnetism of an object as a result of an external influence. When it is in the magnetic field, it will behave like a magnet. Now it's a permanent magnet, then an iron bar is there. When an iron bar is brought closer to the permanent magnet, it would create opposite pole on the nearby side. For example, this is your south pole, so end x of the iron bar would behave or it would create opposite pole, and end y would have the like pole. That's why it would be attracted. But if you replace it, I mean, if you uh, alter it, let's say this is the same rod, and its end x is over here, y is over here, and now you brought a magnet in such a way that its north is here and its south is there. So what will this iron do? Iron will produce south over here and north over here. It would be attracted by all means. So it induces its properties depending upon the end which is brought nearby. So remember this thing, that when a magnet is brought near the iron rod, the rod becomes an induced magnet with one end nearer the magnet having opposite polarity to that of the magnet. Thus, induction always proceeds attraction. This is very important thing, that induction produces attraction. Then we have the next slide, that is state the difference between the magnetic and non-magnetic materials. That is that here we are going to test the materials. There are several materials. I stated that there are three types of materials, right? One, they are magnetic materials, I mean permanent magnet, right? Second, non-magnetic materials, they cannot be magnetized, right? Non-magnetic materials. Okay, And third, they are magnetizable materials. Magnetizable, we can magnetize them. Magnetizable materials. So these are three classifications of your materials. Now, testing of the evidence of the magnet. If you are going to bring the specimen, which is basically the subjected object, near the bar magnet, if it is attraction, then sorry, if it is repulsion, then the specimen must be a magnet. Remember this thing, this is very important. Repulsion is the test of magnetism. If there is an attraction, it is not a evidence that it is a magnet. It can be iron, okay, but yeah, are you getting it?
Yes.
Only repulsion is the evidence that object is a magnet. If there would be no repulsion, it means that it can be iron, or it can be but it cannot be a magnet. So here are some specimen or materials for which I have to explain. A bar magnet, one end of the specimen brought near north pole, then north and north repel, or south is attracted towards that. Then when we reverse it, south pole will attract, or north pole would repel. It means when you are going to bring a bar magnet near a bar magnet, then what will happen? On like poles repulsion, and unlike poles attraction will be there. But on the soft iron rod, north pole is attracted and north pole is attracted. If you have north pole near the end of the specimen, it would be attracted by both ways. Wooden rod, no attraction, nothing happens, right? So here describe the electrical method. I mean, here we are talking about methods of magnetization. Method of magnetization and demagnetization. Here there are two main methods which have been described here in this slide. Magnetization and demagnetization mean by stroking method. Stroking method is very common. If you want to catch a screw with a screwdriver which is not magnetized, so what do? You rub that uh, screwdriver on the magnet. If you have a magnet, or if you have any magnetic material, you rub it over there. When you rub it over there, it catches the screws. This is stroking method, right? So if I have a steel bar and I want to make it a magnet, it is just not a magnet. So I will rub it with a magnet, a permanent magnet. But this stroking and rubbing have a slight difference. That slight difference is stroking, you have to start rubbing from one end and you have to leave the other one. You are not going to rub haphazardly or randomly one. I mean, you are not going to rub in this way. No, it would not create any effect. You have to stroke it. Just you make your sword blade sharpened like this. You start from one side and leave from the other. So this makes the opposite polarities on the material you are going to make a magnet, right? So when you are stroking by two hands, what will happen? When a south is stroked, which end, the end at which south is stroked, it gives you a north, and the end at which north is stroked, it gives you a south. Okay.
Yes.
Okay, now this is an electrical method. This is very important method, magnetization method. When we you have to use a direct current, very important. You have to use DC, direct current for magnetization, right? Direct current mean connect a coil with a DC battery, a voltage source, and with a variable resistor, and place a steel rod inside it, and switch on the current. When current would be flowing through this coil, you know what will happen? One end of the steel bar would become north and the other one would become south. So during magnetization, keep it inside and it would be north would be I mean if this is the north of your coil and south of your coil, then there would be the north of this bar magnet, sorry, bar, and south of this bar would appear over here. So this is the magnetization method. But when you demagnetize that, just do it in the same way but with an alternating current, right? Keep it west to east, switch on the alternating current mean which is having variable value voltages, not battery, babda, and then drag it out. What to do? Drag it out slowly. Due to that, what will happen? It will be demagnetized. So you have to remember this method of magnetization and demagnetization, that in magnetization method we use DC. Please keep this with you. This is very important information. Keep DC for magnetization, right? Magnetization, DC, and then keep it inside, increase the current, and after some time it would be magnetized. But for demagnetization, use alternating current and drag it out, and after some time it would be demagnetized. And then heating and hammering are also the procedures for demagnetization. Then this is describe the plotting of magnetic field. This is also very important and very examiner favorite topic, that when you are going to use the magnetization process, no, sorry, drawing the magnetic field. So how to draw that? The magnetic fields are the region around a magnet in which the magnetic effect can be detected. That is called magnetic field. So the pattern of magnetic field can be plotted by using a compass. This is actually very, dis- detailed slides. For example, here a north pole is there and a south pole is there, and on north pole I will place a compass. This blue, this small circle is the compass, and where the pointer is pointing, a needle is pointing, I will plot a spot. I mean, I will mark a spot over there. Now I will position the compass over there, and I will spot another dot where its needle is pointing. Then on the edge of the needle, at the edge of the square spot, I will place it third time, and I will mark a fourth dot, and then so on and so on. You will keep on plotting these squares and so on. Now you will draw the magnetic field line from north to south in this way. This is the method to draw the magnetic field lines around a bar magnet. Right here, all the magnetic field lines of force show the following properties. They outside the magnet, the line starts from north pole, and at south pole they are ended up. Within the magnet, they come from south and end up at the north. This is very important. They make a close path this way. Check this one out. This way, right? This way. So inside the magnet, they are from south. They are directing from south and ending up at north. But from outside the magnet, they are generating from north and ending up at south. Got it?
Yes.
Okay. The next is the lines can never cross each other. This is the other property. The lines are the lines are closer to each other. When the lines are closer to each other, it means stronger the magnetic field. But when the lines are separated from each other, the magnetic field lines are weak. Sorry, magnetic field is weaker. So here at A, strong field, and at B, weak field, and at C, uniform field. So remember this thing. Okay. So more electric field patterns are there. For example, you are going to bring two poles closer to each other. One is your north and the second one is your south. So what will you do? You will have the magnetic field lines coming from north, and they would attract the nearby south. they will reach to the nearby south. So this is the strongest portion of magnetic field. Okay, are you getting this thing?
Yes.
Okay, so please be aware of this all, that you are asked that where the magnetic field are strongest and where the magnetic field are weakest. So there, if I have or if I place two north poles together, the magnetic field lines would be out of those north poles, and this will be called null zone, no field at all, right? So combined magnetic fields, there is no field effect, that is called neutral point or null zone. The magnetic compass needle placed at this point will no point not point to any specific direction. It would be basically, confused that where I have to be pointed out. Okay, the magnetic field patterns between parallel magnets. So if we have two parallel magnets, the magnetic field lines would be reaching from nearby north to the nearby south. So this is the magnetic keeping method. Magnet keeping, in magnetic stores, sorry, in the stores where we keep the magnets, we place north above the south, and then for the next magnet we will keep its north above its south. So in this way they contain the magnetic field lines. So here the magnetic field lines would not be available over here, so they will repel each other, so you cannot keep them closer. But here they will attract each other, and that's why we keep them in this way, right? Then which statement about the, now we have started the past paper questions, I mean topical MCQs. Which statement about the magnet is correct? So it can attract the other magnet, it can attract an unmagnetized piece of iron, it can repel the other magnet, it can repel another unmagnetized piece of paper, piece of iron. So which is not correct? Yes, D. Unmagnetized piece of iron cannot be repelled, it is only attracted. This is possible, this is possible, this is possible. Okay.
Okay, sir.
Okay.
Oh, you are back. Well done. Now, a bar magnet is broken into three pieces, three parts, X, Y, and Z, north and south. So, this is the question, information. Sorry, this is the information. This is the which diagram shows the poles in X, Y, and Z. Poles X, Y, and Z. So, if this is north, it would become south, it would become north, it would become south, it would become north, and then it would become south. Okay. So what was the south over there and north at the bottom? Okay. Now north here, if he has shown south and south, it is not possible. North and north, it is not possible. Okay. I think there was something missing from here. Maybe it would be north and north, and then south and south, and then north and south. Probably this one. Some values are missing from here. For example, it is south and north, right? You can place this way, and here north and north, it is not possible. So north, south, north, south, north, south. This would be the right option. That's why he has made this option D correct. So these type of questions are asked to you. I will move on and on, so that yes, this question is frequently asked. A chain of steel nail is the chain of iron nail hung from a strong magnet. The chain are then carefully moved from the magnet, right? Moved from the magnet. One is steel, one is iron. So iron has properties that it would be magnetized easily and then demagnetized easily. So when you will release it, it would fall off, and steel would be remained attached. So what happened to the chain? Both chains fall apart, both chains stay together. Only chain of iron nail falls apart, only chain of steel nails fall apart. So your C would be correct in this regard. Now this is the magnetization and demagnetization question. The diagram shows an iron nail in four different situations. In which diagram will the nail becomes an induced magnet? I mean a temporary magnet. So where will it be? When switch is open, nothing
Hey.
happens. Nothing happens. In A, there is a bar and a bar magnet and an iron is there. So let's say it is north, it is south. So iron head will get south and iron tail will get north. But if it is an iron and iron nails together, nothing happens when you place iron nails together, because it is not having induced magnetism. So that's why it is A. Okay.
Yes.
Okay. This is the theory. The end X of a metal rod attracts. Oh yes, this is good question. And X of a metal rod attracts the north pole of the compass needle. What does this show about the rod? According, it could be made of a copper, but not a permanently magnetized. It could be made up of copper, but a south pole at X. It could be made up of steel, but it is not permanently magnetized. It could be made up of steel with north pole at X. Okay. This is what end X of a metal rod. This is a metal rod. It is its end X, and let's say it is at Y. And this is a magnet whose north pole is over here, south is on the other side. So if it is attracted, right, it is basically
It
attracted.
is C.
It could be made up of steel, but it is permanently so, but is not permanently magnetized.
So it can attract.
Yeah, it can attract, right? It could be made up of steel, but with a north pole at X. No, if it is north pole, it would repel. So it is gone. It could be made up of copper, but it is not permanently magnetized. Copper is a non-magnetic material, so it never
Yeah.
attracts or repel. It could be made up of copper with south pole. No. So it is made up of steel, but it is not permanently magnetized, because steel can be attracted. If steel is a I mean, alloy of iron, that's why it has some magnetic properties. So we can say that if it is not permanently magnetized, but it can attract it. Okay. Oh yes, an iron nail can be magnetized by using a coil. Okay, this is an iron nail, it is placed inside and it is being used by a magnetic coil. How can the nail be demagnetized? Leaving apart Leaving the apparatus switched on for a long time, removing the nail from the coil while using an alternating current, using a coil with a fewer turns, using more cells. Demagnetization. Using more cells, no. Using fewer turns, no. Leaving the apparatus switched on for a long time, no. I told you
AC
only
circuit.
one thing, alternating current. Okay. Yes, the diagram shows how a steel bar can be demagnetized. Steel bar can be demagnetized. There is a steel bar inside the coil, and you have a DC power source. So you want to magnetize that. Switch the Which statement describes how the steel bar can be magnetized? This is very important question. This is a complete magnetizing method. So reverse the DC supply. Uh, if you have AC, then cut it out. C and D are gone. Reverse the DC supply and gradually decrease the current. No need to reverse. Reverse the DC supply and gradually increase the current in the circuit. Okay,
Okay.
are you getting it? Oh no no
Yes.
no no. Sorry. Oh my god. Oh,
This was for
wrong.
demagnetization.
Yes, it is demagnetization. My God, after these much classes, magnetization and demagnetization mixed, gone mixed. It is
Then it's
demagnetization. So don't cut
D.
AC wala. So the cut these two, and then you have use an alternating current supply and gradually decrease the current in the circuit, and use an alternating current in the gradually increase the current in the circuit. Yes, D. Okay, when you will decrease the current, actually it would keep the magnetizing properties over there, and then you have to drag as well. A permanent magnet can be demagnetized by using a solenoid with switching the current on, on then off. Which diagram shows the most effective method of producing demagnetization? So here are these four procedures, and it is very important description as well. So option D is correct because magnet is withdrawal without switching off. You are going to close the switch with an alternating power supply, and you are going to draw the magnet out. And when you are going to draw the magnet out, actually it would be getting demagnetized and so on, right? So yes, this is all. Yeah, this was very important question because these type of questions are asked. I was not getting this question over here. Four plotting compass are placed near a bar magnet. You may ignore any effect of the Earth's magnetic field. In which position does the compass appear like this? This. Okay. So as I told you, that magnetic field lines start from north and end up at south. So here it would be something like this. It would be something like this. Similarly, the magnetic field lines appears from north and they reach to the south this way and this way. Okay. Now, if I place a magnet at A, first let me explain you at A. So at A, the magnet would have north in this direction and south over here. In C, sorry, at D, it would have north at this direction and south in this direction. So these two options are gone. At B, if I get magnet over here, sorry, this magnetic field over here, it means the pointer needle will be upward. And similarly, if I consider that the magnet is at C, then pointer needle would be downward, probably downward. Exactly, it is not that it would be exactly downward, but it is in the downward direction to somehow. Okay, is it clear to all of you?
Yes.
Okay, so
Yes, sir.
yes, again, this is a very good question. Option D is correct for that, but let's explain it together. Four plotting compasses are placed in a magnetic field of two identical bar magnets as shown in the diagram. Which compass is shown pointing in the wrong direction? Oh my god, wrong direction. So magnetic field lines this way, they are over here, and magnetic field
D.
lines this way. Got it? Very good. D. So it means the needle is pointing right way over here. So A and B are correct. And C, the needle is pointing right way. That is correct. So here needle should be pointing this way. So D is incorrect one. Is it clear to you?
Yes.
Okay. Now we have the second lecture. I mean, it is lecture 2 of that lesson. The first one was your lecture 1. Let's have let's have it as a lecture 2. So state the difference between the properties of temporary magnets, permanent magnets, and magnetic material. So this topic leads us where we have to use iron and where we have to use steel. Okay, so remember this thing, that magnetic properties, uh, hard magnetic materials such as steel alloy is called uh, alcomax, and it is mm, uh, and magnador. These are names, no need to remember these names. Okay, but steel is a hard material, so it is hard to magnetize and it is hard to demagnetize. Soft materials, magnetic materials such as iron, right, and metal are relatively easy to magnetize, but their magnetism is only temporary. So this is very important, that if you magnetize the iron, sorry, if you magnetize the steel, steel remains magnetized for a long time. So here I'm going to make a summary of that. Steel, easy to, sorry, hard to magnetize, hard to magnetize and demagnetize, right? But it is used for permanent magnets. Permanent magnets, right? but your iron or soft iron is easy to magnetize and easy to demagnetize. So it is easy to magnetize and demagnetize. That's why it is used as induced magnets, and induced magnets are like core of coils. I will explain it. What does it mean, core of coils? Okay, so you have to keep this slide with you. I will share these notes with you as well. Use of permanent magnet here, where I mean, a lot of questions are asked from this domain of your topic. Magnetic compass is used by a permanent magnet. So we use a steel needle over here, which shows us the north and south. Then the magnetic safe MagSafe chargers, they are basically used, or they are formed from the magnets, permanent magnets, and they are used to pin the sockets easily. Then fridge magnets, like they are used to close the door, or some sort of materials can be used to paste on the refrigerator door. Mm, right, there are some sort of decoration pieces like that. Then this is very important, the permanent magnet generators. There are some devices which are your generators, AC generators, they are power generators. They are used permanent magnets. Then dynamo in your cycle, when you um, rotate the tire of your cycle, it produces light. That uses the permanent magnet. Then use the permanent magnet is used as a tip of this screwdriver, as I told you. Then we use the door catcher or door holders. They all are your permanent magnets. Then use of electromagnets. These are the electromagnets. Here we use iron as a core. So an electromagnet is switch operated by a relatively small electric current that can be turned on and off with large current. For example, these are the coils. Actually, these are the coils, and relay is asked to you. This is very important device. What is the function of relay? An electromagnetic switch operated, which uses small current. Small current, I'm just writing it as the examiner report, or as the markings. It uses small current and handles large current, and handles large current. This is the function of a relay. Further details will not be provided yet, but you have to consider that it uses very small current and operates very large current, just like your AC relays. You are going to operate a relay with remote control. It uses a very, I mean, zero point 0.5 milliampere current, but it operates the motor of your AC. It's huge current, almost 13.6 ampere current. So by using relay, we perform that procedure. Then in speakers, I believe that you people are known to these all. Speakers are used. Speaker uses permanent magnets as well as electromagnets. So what happens, due to the alternating current operated in this coil, the repulsion and attraction of this coil happens, and then it causes the vibration on this diaphragm, and that's why the sound is being produced. Then we have this doorbell. This doorbell is using electromagnets and some sort of permanent magnets. So that is a hammer. So when alternating current, when you press the switch or when you close the switch, alternating current is basically provided into these coils, and due to that, they attach, or they attract this hammer. I mean, this this drum is this drum attracts the hammer and releases it periodically. That's why we it's basically hits it so frequently, 50 times a hertz, 50 times a second. Then maglev maglev trends. This is our very giant technology of the magnets. We suspend very heavy loads by balancing the magnetic fields, just like your train. So magnetic levitated trains driven on the magnetic levitation. Levitation means suspension. Okay, the the is a transport method that uses the magnetic levitation to move the vehicles without touching any ground. It reduces the friction significantly. That's why they are very highly efficient. But there are some disadvantages of these as well. Then we have to grasp or grab the material scrap correction. Here we use the electromagnet. For example, when we want to lift these heavy loads from the shipyard or from any scrap, so we switch on the electromagnet. It attracts all the irons, it attaches them together to with this electromagnet. There's a coil inside, and when you want to unload them, you open the switch, and it would release all these iron pieces. So this is very powerful tool, scrap collector. Then magnetic resonance imaging, MRI. It is just to tell you that we use MRI on the basis of its magnetic properties in our body. Hydrogen atoms are there, and they are being resonated by using magnetic field, and then we can image, or we can proceed the image of the person, that what problem or abnormality do we have. Then explain the charge of the material for the use of magnetic screening. This is also an important topic. Screening means to prevent the effects of external magnetic field. Magnetic screening is a method of re- redirecting the magnetic field lines so that the magnetic flux flows through the walls of the shield itself. Most steels are used as its work well for the redirection. Do you know that the hard drives of our computers are fixed in the steel casing? Do you know
Yes.
why?
Yeah,
Hard
because
drives, hard disk.
hard drive is made of tiny magnets.
Yes, that is cased, or that is safe inside the steel. I mean, if I have a small device which
So
I've
then it's
think
in
that
charge.
it would be protected from the external magnetic field, then I will protect it from the steel casing. Then what will happen? This steel will redirect the magnetic field lines in such a way that, for example, this is north, this is south. So what will it do? It would make itself, or it will divide itself into two parts. This would behave like south, and this would behave like north. So it would attract all the magnetic field lines coming from the north, and then this next part would provide all the magnetic field lines to the next north. So in between, the material is safe. This is amazing. Okay. Then the purpose is to prevent the magnetic fields from interfering the electrical devices. The magnetic resonance imaging equipments, right, are powerful magnetic flux speakers. Magnet can destroy the cathode ray tube television picture. Oh, ah, I can tell you a very interesting fact. If you have a CRT monitor, old monitor at your home, right now we all have basically sold them in scrap. But if we have them, these bigger monitors, and if you have a magnetic speaker, I mean simple speaker, and you want, if you just keep it closer to that and just move it for back and forth, it would destroy the picture. I mean, distort the picture, right? So this is what the magnetic storage materials, these are used to sorry, magnets are used to prepare these, for example, your hard drives, your speakers, then your no, not speaker, basically these are your cassettes, right? I don't know. I forget the spellings, but we were using the cassettes, magnetic cassettes. Then this ATM card. Nowadays, this is very common thing to consider that how do we prepare that. Then recording tapes are being they were being used by using magnetic properties, right? There was a magnetic material. Yeah, this one. There was a magnetic material. It was uh, I mean, magnet was grind into small pieces. It was a paste or emulsion was prepared, and that emulsion was pasted on the plastic tape. Now that was a cassette, recording cassette, and then we record the signal by using a tape head. Tape head is nothing a coil, but so it releases the magnetic field lines over here. It is its north, it is its south. So due to that, this is what the tape motion. This is the recorded. Okay, this is recorded zone, and the remaining this one what is coming behind, it is unrecorded yet. So when we will when it would flow through this magnetic field of the internal circuit or the internal current, then it would be recorded, it would be basically magnetized. So these are some sort of behaviors what we discuss in our or what we use in our magnetic material, or what is the use of the magnetic material. Now we have lecture number 3. If you people have a bit time, I would like to complete it. Especially Ariba, do you have few 5 to 10 more minutes or not?
I do, sir.
Oh, very good, because I'm bound for your next class that you have to be released in time. That's why. Otherwise, Yahya and me can stay till 11 o'clock. Yes, Yahya? Are
Yeah.
you? If Ariba says that, okay, I'm free till 11 o'clock, then will you stay?
Okay.
I know, you are tired enough. Okay, this time we have to describe the patterns of magnetic field lines due to current in a straight wire. I have to explain, or I have to tell you this thing, that whenever we have a straight current carrying wire, it would have a magnetic field around it. Then we have to consider a solenoid, right? And uh, then changing the magnetic field direction and current in that. So this is actually the start or beginning of electromagnetism. Electromagnetism is to prepare a magnet with electricity and wires. It is to prepare a magnet with electricity and wires. Okay, so electromagnet is basically at the end of this topic I will tell you that actually electromagnet is just like a magnet, nothing difference. Now the magnetic field around a long straight wire. Questions are asked to you. If you have a straight wire, right, and you make a hole in a cardboard and you spray some iron filling on that cardboard, and you provide current in this wire, then you will observe a strong or a strange behavior, that all these iron fillings would become circular like this. They would accumulate themselves in a circular pattern. Okay, are you getting it? Now, after that, we placed a magnetic compass, and we came to now that the magnetic field lines are actually this way. The magnet needle would be pointing this way, and this way, and this way, and so on. So with the help of this, we came to a conclusion that if we grip the wire in such a way that the direction of current is in our in the direction of our hand, then curling of finger would be basically pointing the direction of your magnetic field. Is it clear? So if you grasp the coil, sorry, if you grasp the wire in the direction of current, right? Imagine gripping the wire using your right hand. The thumb points in the direction of current, and the finger curl in the direction of magnetic field. So this is called your framing right hand grip rule. What is that? It is flaming right hand grip rule. Then if you reverse the direction of current, the magnetic field lines are reversed. Remember this thing. If you reverse the direction of current, direct current is upward, so magnetic fields are anti-clockwise. And if you say that current is downward, so magnetic fields are clockwise. Okay, if current is upward, so field is anti-clockwise. And if current is downward, then magnetic field is clockwise. Is it clear to you? Similarly, if I say that if the current is into the page, right, dot shows into the page, sorry, cross shows into the page, current is into the page, it is shown by a cross, and dot shows out of the page. So now point your thumb towards yourself for this one. For this one, current is out of the page. It means the curling would be pointing, our fingers would be pointing this way. Ariba, will you
Yes.
try this with your hand? Do you see your screen?
Yeah.
So if I tell you that here the current is coming out of the page, out of the screen, so can you point your thumb in towards your eyes?
I suppose I can.
Yeah, you can, exactly. Then where is the direction of your curling of finger? Is it clockwise or anti-clockwise?
I think it's anti-clockwise.
Really? Isn't it in the direction I have shown these pink
Yeah,
arrows?
for me that's
Yes.
anti-clockwise.
It is how you apply the field, sorry, you apply the grip rule, right? And yeah, you have to perform this for
Yes.
into the page. Point your thumb into the page, into the screen. Then tell me whether your curling a finger is in the direction of these arrows or not.
Yeah, it is clockwise.
Clockwise. So just a conclusion here. Conclusion is conclusion is where is the conclusion? I have to write over here that into clockwise. I mean into mean cross clockwise. Okay, and cross means into, dot anti-clockwise. Okay, and dot mean out. Now will you be able to remember this? Because questions are asked to you from this topic. Should I move forward?
Yes.
Okay. Now, the field of a flat coil. Field of a flat coil is basically when you have uh, a coil, you make two holes in a cardboard and you just put a wire, circular wire over here. The wire is coming out of this side and it is getting into this. So if you grasp this end, will you have these anti-clockwise field lines? And if you grasp the uh, this end, let me call it end B and let me call it end A. If you grasp end A with your right hand, thumb pointing downward, so will you say that magnetic field lines are clockwise? And here magnetic field lines are, when you are holding end A, pointing thumb upward, right? Pointing the thumb upward, then magnetic field lines are clockwise, sorry, anti-clockwise. Generally, if I say that inside the coil, the field lines are in the same direction. So the magnetic field due to current in the flat coil is stronger in the region inside the coil. The fields from each part of the wires are same direction and confined to a small area. So this is what, this is actually a sort of now we are reaching at the electromagnetism, right? Finally in this round, finally in this round, third round, right? The magnetic field in a solenoid. In a solenoid, if you see that I have made different holes in a cardboard, and all these pink arrows are coming out of the cardboard, and all these green arrows are going down the cardboard. So, if I grasp the coil in such a way that my hands are, oh, the nails are now bloody nails. Okay, so this is what, this is the direction of current which is indicated by your fingers curl. So you have to grasp this coil in such a way that your nails are, fingers are here in this way. It means 1, 2, 3, 4, 5, 6, 7 fingers. You have 7 fingers. No, I'm just kidding. So the nails are here in the direction where the current is entering in that. So where would be the thumb pointing? Either towards A or either towards B. Yes, this is your test. Check this one out. Your nails are pointing in the direction of these green arrows. So, yeah,
Yes.
where will be your thumb pointing?
Right.
Towards A or towards B?
Towards, what to say? A.
A. Remember this thing. Grasp the coil with your right hand in such a way that the current is in the direction of your curling of finger. So when you grasp it in this way, that curling of finger mean your nails are downward, finger are touching the cardboard on this side, then your thumb will be pointing towards A. So A is north and B is south pole. This is what it is mentioned over here, right? So the magnetic field is the stronger in the region of the solenoid. The field lines in this region are parallel to each other, showing that the field has same strength along most of the inner part of the solenoid. So this, if the current in the solenoid is reversed, then the poles will also be reversed. The strength of the magnetic field which is produced in the solenoid can be increased by increasing the magnitude of current, increasing the number of turns, and putting a soft core inside the solenoid. This was the use of iron. So if you graph it, or this is basically the rule to determine north pole. That how to determine north pole. North pole in the coil of coil. So what to do? You have to use right hand grip rule that can be used to remember the direction of magnetic field. Curl the finger of right hand in the direction of current, then thumb would be now pointing towards the direction of magnetic field. It points towards the end of the solenoid that behaves like a north pole. Are you getting this? That here, if you have a coil and you are going to grasp the coil in such a way, let me draw this in this way. I have a coil and I am going to draw this coil in this way. Okay, so when I'm going to draw this coil, so the direction of the current is downward this way. So current is getting up from here, current is getting down from here. It means I have used positive and negative over here. So this points north pole of the coil and this points south pole of the coil. Now is it clear to you?
Yes.
Or should I change the color of this coil? This way. Okay. Now this is that coil. I have drawn it for your convenience already. I was teaching a class. So this is that coil in which I have grasped that was grasped by with right hand. So my curling is in the direction of these green arrows, right? So where would be the thumb pointing towards this north? I mean towards this right. So that right is north pole and left of the coil is south pole. So magnetic field lines are inside the coil, and those magnetic field lines are basically from south to north. I explained you earlier that in the permanent magnet, the magnetic field lines inside the magnet are from south to north, and from outside they are from north to south. So we will explain this all over here. Right, let's say I'm going to prepare a coil, and then I will be winding up this lesson today. This is positive and negative pole. So if I say that current is going in this direction, so on all these front edges, the current would be in this way. So you are going to grasp the coil with your right hand. So this end becomes north and this end becomes south. So if you draw the magnetic field lines now, the magnetic first draw the central one, then draw the lower one or upper one. And inside, draw the magnetic field lines in this way. And outside, if it is mandatory, if it is asked, then complete it from north to south this way and leave this central one alone this way. This is how to draw the magnetic field lines inside a solenoid. Okay, is it clear to all of you? Here are some
Yes.
uses: magnetic relay, magnetic circuit breaker, loudspeaker. There are so many things. I would explain this, and then we have past paper questions, right? And I believe that this would be clear to you. In next lesson, inshallah, we will be starting from the uses, and yes, I think uses would be just, I will quit these uses for the end of your chapter, that where do we use these relays and how do we use them, right? I will start with the next chapter, I believe so. Okay, sorry
Okay.
for this much long class, but I tried my best to uh, engage you people as much as possible because I had some time today. That's why. Do you have any question?
No.
No?
No, sir.
Oh my God. Will you not say thank you to leave you people?